in network theory, in particular from the sub-community in network theory coming from statistical physics, understanding how it is possible to change resolution in a network. What does it mean? Typically, that's the main, one of the main source of this kind of studies. Typically, the resolution scale of a network, of a real-world network, is not an intrinsic scale of the system, but it's something due to our limitation to observe the system or to collect data, or for convenience to coarse grain data from the beginning. Imagining epidemiological network, it can be just a single individual, it can be a classroom in a school, it can be a city, each node, and the link also is a certain number of flights, a certain number of commuters from one town to the other. So the contact links are also matter of definition depending on the observational tool and collection. So we would like one of the fundamental issue about so the real world network, what are the intrinsic scales that characterize the system and the dynamics running on this kind of irregular space. So imagine you have a process running on, in the network is a space of embedding of a process, how the dynamics depends on the resolution scale. So in order to answer this question, we need to find a way to change scale and to see what is conserved, what is not, in particular to find a change of resolution scale, a coarse grain, we would say in statistical physics, so that large scale features of the system are conserved. So there is a problem that I cannot change the slide. No, I can from here. So in general, if some of you go to a conference in network theory, you will see that most of the talks will divide in two kinds of talks. The first one deals with the structural topologies of real-world networks. Clearly, you have graph theory mathematics as a mathematical support, but clearly big, irregular, heterogeneous networks are difficult to be the subject for graph theorems. So something can be done, but most of them is heuristic, and you need some heuristic new mathematical tools to classify the network. And that's why in many talks you will see that people looks for the hierarchical organization of the network, if there are multi-scale features, and introduce new methods like in order of complexity, the degrees distribution is the first measure of complexity of a network. Then the nearest network connectivity is the first source of correlations, and then clustering, and then community detection, etc., etc. So you see that most of the, more than half of the talks are about some topics like that. Then there is another part of the talks in conferences on networks dealing with dynamical processes running on networks. For example, epidemic or synchronization processes in which the nodes of the network, the vertices of the networks are the units that either synchronize or infect. And so the typical study in this, for example, around the world, etc., is to understand how how can we say, to study the interplay between the topological complexity of the embedding space and the dynamical roots of the model. This is something new because typically models in statistical physics were embedded in regular spaces, either Euclidean spaces or regular lattices. And so the topology is simple to understand. The role of topology is reduced to few parameters: coordination number, dimension, spatial dimension, and this is enough to understand the phenomena. While we clearly know that the topology of a network characterized by many parameters, and each of them can be important. Okay, so if you want to study an epidemic process on this kind of space, we know that that's difficult to understand where changing the strength, the R0, if you remember the COVID period, the R0 and the duration time of the infection, you like to know what happens in terms of spreading of infection on a space like that. And this is very, very, very difficult. At the moment, only numerical results are available for real-world networks. They're very important. There are very big computers working only for this, for example. Or if the same problem is, if we want to understand the synchronization dynamics in a brain networks as complex as this one, even more complex than this, how the global brain or finite portion of that synchronize, the neurons synchronize in order to satisfy some external conditions. In physics, in statistical physics, when you want to know what happens when you change the scale of a resolution of a system, you immediately think about the renormalization group. That was the tool introduced between the second half of the 60s and the beginning of the 70s, and then developed for the next 20 years in statistical physics to change scale in the physical model, embedded in regular spaces, typically, with the requirement to conserve the large scale properties. What is the best way? So imagine to have, for example, the Ising model, so for the statistical physicist, a system for magnetic interaction, and you want to conserve the large scale property. This is particularly important when the system is close to a phase transition, when the only important and the characteristic length scale is the correlation length internal, which has nothing to share with the resolution scale, which is very far away. And you would like then to get rid of the resolution scale and just keep the physics around the characteristic scale. And so this is the way in which you are able to treat this problem to uncover all the critical properties of the system. So in some way, in the last 15 years, many colleagues in network theory, in particular coming from statistical physics, try to generalize this kind of approach to irregular spaces like networks. The normalization group can be seen as the composition of 3 steps. The first one is the coarse graining. This means partitioning the space in equivalent cells, introducing macroscopic variables for each macroscopic cells. Then, let's do this one. A second. Redefining, if you have a model on the network, redefining the coupling constants for these macroscopic variables, and then rescale the spatiotemporal variables so that you want to conserve, I don't know, the physical properties of the system at large scales. In statistical physics, the second and the third steps are the diffuse ones. While the first one, typically, when you have spatial homogeneity, is quite simple, is immediate, as we will see. This is not the case in network theory. In network theory, where seen as an irregular, heterogeneous, small world space, the first step is the diffuse one. And most of the works in generalizing, aiming to generalize the normalization group in network theory focus on this point, how to partition the space and introducing macroscopic variables that can be considered in some way equivalent, so that I can collapse all the macroscopic variables inside in single mesoscopic or macroscopic variables and introduce an effective systems that conserve the physics at larger scales. Okay. So, for example, in Euclidean space, in a regular lattice, two-dimensional lattice, the definition of identical sets is clear. You partition the lattice in identical sets. There are microscopic spins or microscopic variables. You introduce a mesoscopic one by taking the average or decimating in some way the microscopic variables in each cell. And then now the problem is to understand how these microscopic coupling, the links here, become these mesoscopic ones. What are the right way to do this? So that the diffusion is there. Once you have solved it there, and then you rescale the variables, you perform the renormalization. The most important result is solving the problem of second order phase transitions and to understanding the state of scale invariance, which separates the low temperature ordered to this large temperature disordered phases. In this separating status, you have a scale invariant as a fractal, is a scale invariant system in which so that the intrinsic scale is giant so that you can get rid of the macroscopic details. And through the normalization group, you can understand what happens when you are passing from here to here or vice versa, passing through this state. What are the velocity of divergence of this correlation net? That's basically okay. In heterogeneous network, as I was saying, the first problem, the spatial and topological heterogeneity is the main obstacle. And in particular, the small world property is a big obstacle to extend the normalization group program. Even if the couplings between nearest neighbor at the microscopic scale are the same, are homogeneous, the fact that the topological connectivity is highly fluctuating and that there are connections which can be considered long range makes very difficult to introduce the concept of equivalence of cells of mesoscopic. What does it mean to say they are equivalent? So all the different papers you will find in literature try to introduce a definition of equivalence that can be geometrical, topological, can be physical, and following this recipe, partition the space in cells and coarse graining. So, for example, just to give you, in the particular case of planar graph like this one, in some sense, it is even though it is not a regular lattice, a regular space, you can resume some metric criterion to partition the space in equivalent regions. Okay, and that's in the generalization of this for networks that are not planar but can be embedded in appropriate curved space, for example, developed by Bogugnà and Serrano, like grounding on some works by Tommaso of some years before, in a very important, very nice formulation of the normalization. Then there are other techniques, for example, based on fractal structures, for example, Radicchi et al. or even other kind of. So there are many papers. Each one takes an arbitrary definition of equivalence of cells of a mesoscopic region in order to perform the coarse graining. So in this talk, in this first part of the talk, I will talk about our definition that you can consider arbitrary, but I will show you that it's a direct generalization of the approach used in statistical physics. Okay, so our method is based on a simple and very important operator for networks, for undirected in particular networks, that is the symmetric Laplacian matrix. The symmetric Laplacian matrix is defined by the adjacency matrix of the network, so the matrix giving the connection between pairs of vertices in the network, and the diagonal, the degree matrix. So a diagonal matrix in which on the diagonal elements you have the number of for node I, you have the number of neighbors of node I, so the degree. Okay, so the sum, which is the sum over the row of the matrix itself. So that if you sum over the rows or the columns, this matrix, you get 0. This is in graph theory, it has been introduced as one of the two most important discretization on networks of the operator, the differential operator minus nabla square. Okay. Why minus? Because mathematician likes positive definite operators, not the negative definite. That's why it minus. But that's the only reason. And what are the fundamental properties? Just give you, so this for undirected network, this is a symmetric matrix. So you can apply the spectral theorem. All the eigenvalues are real, and eigenvector can be chosen to be orthogonal and form a complete basis. And in general, in the eigenvalues, are non-negative, and the number of zero, or the eigenvalue zero, so the dimension of the kernel is the number of connected components of the graph. If the graph, as we will consider, is simply connected, you have just one eigenvalue zero. And the eigenvector corresponding to this zero eigenvalue is the uniform vector, 1, 1, 1, 1, 1, over all the vertices. Okay, this means that the final status of diffusion is uniform. How we use this operator? There are in literature thousands of papers about spectral clustering of networks using Laplacians, and most of them study the spectrum of this operator, the eigenvalues and the eigenvectors, and usually collapse in a principal component analysis. Let's take the first 2 or 3 eigenvalues and eigenvectors and project the network over these eigenvectors, and in this way we find the principal components of the network. If your network has 100,000 nodes, vertices, it will have 100,000 eigenvalues. And if I ask you, what's the meaning of the 120-second eigenvalues and eigenvector, no one is able to answer. What's the physical meaning? What's the geometry? Because this is due in regular spaces, you know, it's the plane wave with this frequency. But in a network, due to the irregularity, the heterogeneity, the information, the geometrical information embedded in this eigenvector is quite an obscure object. That's why instead of using the spectrum, we use this is the diffusion, the heat equation, the diffusion equation on the network, whose formal solution is this one. We use directly this operator that in physical terms can be seen as the green function of the heat equation or the propagator. Okay, so or simply the time evolution operator of the. So if you have an initial status for a diffusive field, a concentration field, for example, the information field over the nodes, over the vertices of the network, this is the vector at time t, following the simple diffusion equation. Since this is L is a median, it is also a median, it's positive definite, and you can use due to a medianity. Is it English medianity or medianicity? I don't know, it's medianity, I think. The medianity, you can use bracket formula, the formalism, Dirac formalism, in order to decompose vectors and operators on the basis of eigenvectors of this operator. And in particular, at each time t, you can introduce a measure. So the matrix element, so let me go. The matrix element of this operator is simply the fraction of information of diffusive field flowing from node I to node J in time t and vice versa. That's the physical meaning. That's the difference with the singular eigenvectors. At each time, it contains all the powers of that if you use Taylor extraction. The physical meaning is clear. It's simple. It's the simplest possible. Okay. And through this, if you introduce a normalization, the trace of this operator, so the sum of the numerator over all the possible eigenvalues, you can introduce a statistical weight of the health mode or eigenvector in the configuration of time t. Okay. First of all, let's see how we can formulate the ordinary renormalization group in statistical physics by using this operator. On regular lattice or regular spaces, this is L is simply minus W squared. The eigenvector, the eigenvalues are K squared, and the eigenvectors are the plane waves. Okay. And this is the diffusion equation. We can use, in order to define block variables and identical cells, the relation between the wavelength or the length, diffusion length, and the diffusion time. You know that the diffusion length squared is proportional to time. Okay. And so the characteristic wave mode at time t is simply related to t by 1 over t. Okay. In this way, we can use t as a scale parameter to define the characteristic plane wave or the characteristic size of the cell renormalization cell. So the T is a scale parameter. So in statistical physics, you need in the normalization a scale parameter that you move continuously in order to determine the flow for the normalization. So we just adopt the same approach, just substituting minus nabla square with L. And in this way, this time evolution operator, this green function defines at each time equivalent macro nodes of the same wavelength. Okay, just to give you what's the work, how this operator e to the minus TL appears in the network. Let me show you the time evolution. This is the matrix. This is okay. How we take a stochastic block model. Stochastic block model is a network composed by a certain number of families. In the picture there are 5, but here there will be 4, in which are densely connected by internal edges, and we have a much sparser amount of interfamily connections. Okay, so at the beginning, the operator e to the minus TL takes 0 everywhere. Okay, and this one just along the nodes. So at the beginning, you just this line, then so there is no connect. It doesn't reveal any connection, but as time goes on, it reveals all the connections and progressively. So at a certain short time, the single families, and then they take connection to these families. So, okay, this is not really fascinating. It's a simple case. Let's go towards a much more difficult case. This is a hierarchical modular network with a core periphery structure that has been introduced to mimic the hierarchical organization of the connector. Okay, so it is some way similar to the previous simple model, but now each of the blocks is decomposed again in a stochastic block model, then again, and then again, and again. So it's very difficult. It's a hierarchical modular structure. So let's see what happens in this case. So the matrix rho start to localize of the structure as time goes on, and there is mutual organization. So all the structures, the intrinsic structures of the network are written in the matrix rho. Okay. You can see this operator to minus TL as a sort of Laplace transform or Fourier transform. When you have a strange signal containing structures that are difficult to reveal, the first thing you do, you apply a Laplace transform in time or Fourier transform in space. And then from the peaks of this Fourier transform, you reveal the characteristic scales and the structures. Okay, this does more or less the same, but in operatorial space. Okay, let's go. For example, this is the brain. So there are structural organization, there are the two spheres appearing very slowly, and all the internal organization in terms of fiberness versus fibers appears. And at the end, there are interconnections between the two hemispheres through the corpus callosum and the deep cortex. And at the end, you get okay. Okay, so we see that if we are good enough in using the information encrypted in this operator, we will be able to uncover the different scale and the structures, and also to renormalize, to resolve at different scale the system. So a direct generalization of the Wilson formulation renormalization group in K-space can be done in the following way. So if you remember, so Wilson renormalization group for dummies. So you write your theory in K-space, because why in K-space? This is a good question for an exam. In K-space, because typically both the space of embedding and the interactions are translational invariant, always the same. And when you have translational invariance, you use as a natural basis to represent the system the Fourier basis, because the Fourier basis is the eigenvector of the translation operator. Okay. So you take this and then you divide large wavelengths from small wavelengths. You integrate out the small ones, and then you change scale of resolution, and then you see what happens when you get rid of the small scale details. Okay, so we do the same. We take the eigenvalues of the operator L, and we divide with these are the small, the slow ones, the large wavelengths, the small eigenvalues, the large wavelengths, and these are the fast wavelengths. We integrate out, eliminate this one from the theory. So we move from the original Laplacian to this reduced one. So the original Laplacian, we have the sum from 1 to n, all the eigenmodes. And we cut the fast ones, and we say, okay, this can be seen as the Laplacian of a network which is smaller with micronodes, in which you have changed the scale of resolution. Clearly, this is not simple. In general, in the Wilson formulation normalization group, you don't need to talk about the real space. You have a theory, you're using model, you write in K-space, you work directly in K-space of the calculation up to finding the critical exponents. Okay, but clearly we want in network theory to have also a real space interpretation of what we are doing, because visualization is very important for networks, for their irregularity and heterogeneity. So what does it mean? What does it mean to do all this machinery from the real space property is important. So clearly there is not an exact mapping in real space. When you integrate plane waves, what happens in the real space is not simple. Okay, but you can have an approximate picture of this. For example, you can do this. You can take your macronodes, you have your original nodes at microscopic scale. This is the scale parameter fixed at a given value. So the diffusion time fixed at a given value. You order this matrix element in decreasing order, and then you start to collapse, to coalesce the different nodes, starting from the mostly connected to the up to reducing the size of the networks from n to n minus m. And then you sum up the original microscopic links that connect macronodes in order to get a weighted but undirected mesoscopic networks. So this is an approximate way, for example, to represent this. Just to give you the relationship with statistical physics, field theory. When you have a field theory, you have, this is the Hamiltonian. This is the Hamiltonian, and typically the Hamiltonian for all theories in statistical physics and also field theory, also in particle physics. Typically the Gaussian approximation, so you have a Gaussian part, so a quadratic part, and then you have a non-quadratic part. The quadratic part is always determined by the Laplacian. It's always the Laplacian plus a mass, and if you have a spatio-temporal field theory system like epidemic, you have also the linear time derivative, so the diffusion equation. So it's always the diffusion operator plus the mass. Okay, it's always that's why we decide. That's why Wilson decided to use K-space, because this quadratic part, this Gaussian theory, is diagonal in K-space, and so you can solve immediately. The integrals can be done in 1 second. So you have a zero-order approximation of your exact process that is exactly solvable. You can hope to treat all the rest of the non-Gaussian interactions with perturbation theory in some particular epsilon expansion, close to a critical upper critical dimension. So there are many other ingredients, but the strategy is this one. That's why they moved for the calculation from the initial real space renormalization group to the K-space one. If you want to have a physical picture, real space renormalization is immediate, gives you the flavor of the normalization. the philosophy of normalization. But if you want to perform calculations and to find the critical response, you need to go to K-space and to do field theory approach. Apart from particular case, one-dimensional beta lattice, the usual very simple cases. In particular, there is a very nice paper by Megangel, Munoz, Uxate, I don't remember the third author, of 10 or 15 years ago on Physical Review Letters, showing that all the models, the spatio-temporal models using statistical physics can be written, can be represented by a functional stochastic equation, so a field theory, which is equivalent to field theory, that takes this general shape, in which you have the Laplacian, the mass, and the non-Gaussian part. This is the non-Gaussian part, plus a noise. And so you see that the basic, so the Gaussian approximation, suppressing this, is a Gaussian process dominated by the Laplacian operator. Okay, thanks to this this formulation, both in K-space or its translation in real space, we are able to start from a network, choosing the state value for the scale parameter diffusion, identifying the subclusters, and then collapse them and getting a renormalization of the network, changing the resolution scale. Okay. How much time do I have, Paolo?
25.
So, 50 minutes. So, let me go deeper in the analogy with statistical physics. This is very, because up to now it's quite simple. It's difficult for calculation, but the idea is simple. In order to build a more solid ground for this architecture, we started to analyze what's the physical meaning of this measure, the measure over at time t, at diffusion, at the value of the scale parameter, the diffusion time at fixed t. What's the meaning of this probability distribution over the modes of the system? Z of t is the partition function, is the time, so it is the time-dependent normalizing weight, normalized vector for the eigenvectors. So for p equal to 0, the initial time, this distribution is uniform. This means that there is no information about the structure of the network. All the vertices contain the same information. They are isolated. We don't. And you know that at time t equal to infinity, or since there is only one eigenvalue 0 and the other are positive, this becomes all the measure collapse in the eigenvector on the eigenvalue 0. This means that if you wait for diffusion a long time, the diffusing field is uniform along your system. This means it is a sort of gigantic macro node, single one. Okay. There is only one structure. In the middle, you have a monotonic increase. And then you have a change in intermediate time t. So since this is a well-defined probability distribution, we can introduce the Shannon entropy in order to see how the information about the structure is collected by the diffusion. Okay. Then we note what did we note? The Domenico and Biamonte in 2016, in a very beautiful paper, that realized that this as the structure of a von Neumann entropy in quantum statistical mechanics. So the same quantity can be written as minus the trace of this operator. And this is the canonical von Neumann entropy, thermodynamic entropy, where T, the time diffusion time, plays the role of the inverse temperature, basically. Okay. To be more precise, this is quantum statistical mechanics. This is our approach. In quantum statistical mechanics, the Hamiltonian is an Hermitian lower bounded operator. That's the fundamental requirement to have a good Hamiltonian. In our case, L is Hermitian and lower bounded. It is not important semi-definite or not. What is important due to the normalization that is lower bounded. Once it's lower bounded, it's well defined. If it's not lower bounded, it's a problem. It's a big problem. Even in statistical, even in quantum mechanics, we know that if the Hamiltonian is not lower bounded, the evolution of the wave function is bizarre. Okay. This is the canonical density matrix in the canonical ensemble. The density matrix in the canonical ensemble. This operator is exactly as the same mathematical structure where L plays the role of H and the diffusion time of the inverse temperature. This is the fundamental entropy for us. This is the Laplacian diffusion entropy. But since this has the same mathematical structure of the thermodynamical entropy, we know that when we have the thermodynamical entropy or also the energy, but we can pass through the entropy, it's very convenient. We can define a susceptibility, thermic susceptibility, the heat capacity, by simply taking the derivative with respect to the temperature of the entropy, we multiply by T. And this quantity has the property that if something strange happens in your system at a certain temperature, you get a diverging maximum in this. So if you have a phase transition, the heat capacity usually have a maximum that diverges in the thermodynamic limit. So this has the same structure. So the diffusion time is a scale parameter. The temperature in statistical mechanics is a scale parameter. It fixes the correlation length. That's the only property of the temperature. Okay, if you increase the temperature, you reduce the correlation length. If you increase it, typically that's the. But anyway, it's a scale parameter. So we have a scale parameter. So we can introduce a Laplacian susceptibility, an entropic susceptibility, so that if we will find some maxima, but pronounced maxima in this function, this means that there is a sort of phase transition, structural phase transition in the system. What does it mean? That the topology, there is a scale after which the topology of the network changes. That's the, for example, in the stochastic block model, you will expect that the characteristic time for diffusion to invade the single block, there will be a maximum. And then there will be a slowdown after the maximum of the diffusion. So each time for each maximum gives you a characteristic scale. And in particular, what happens if you have not a maximum, or you have a flat heat capacity? A flat heat capacity is a strange case. Then you can see that if it is constant, this is possible only if the spectral density of the eigenvalues of the Laplacian are power law distributed, which is a good definition of scale invariance for this. So when you have this is possible only if this is true, and if you have this, what happens is that this value, the amplitude of the capacity, or the heat capacity, or the susceptibility, is strictly related with the spectral dimension. Gives you a direct measure of the spectral dimension, which is related to elastic modes in a graph or in a fractal in the network. Okay. What are trivial scale invariant system under coarse graining? A lattice. When you coarse grain a lattice, you get a lattice. So you expect this is flat. When you get a tree, when you have a tree, if you coarse grain a tree, it's a tree again. You will expect diffusion invade progressively the branches of the tree. So if you coarse grain, you get again a tree. So they are trivially, in some sense, trivial. They are trivial example, but there can be very many others. Okay. Let me show you what happens to this susceptibility in very typical cases. Erdős-Renyi, random network. You connect nodes, pair of nodes in the network with a certain probability, and then without any other criterion, so it's maximally random. Your susceptibility has a single maximum. There is no structure in the system, up to reaching the invasion of the whole system. That's give you the invasion of the whole system, and then there is no more diffusion. This is a random tree. In a random tree, apart from the lower cutoff and the upper cutoff, you have a flat. And what is nice is that the amplitude, this is the scale. The amplitude is 0.66, and it is known that the spectral dimension of random trees, the spectral dimension of random trees is 4/3. So this is also a way to measure the spectral dimension. A direct measure of the spectral dimension. This is what happens when you renormalize a tree. This is a beta lattice, and this is a tree, a random tree. In a random tree, a random tree becomes another random tree, which becomes another random tree, which becomes another random tree, and the spectral dimension stays constant. This is the Watts-Strogatz small world network. So you have imagine to have a ring, so a linear lattice closed with second neighbors connection, so that when you rewire some of them, you do not disconnect the system. So then you rewire a certain fraction of the links connecting the initial nodes, and you rewire randomly. So you create long-range bridges. So this is your networks has two maximum. This is related to the short-range lattice order, and these are the long-range connections. This is the stochastic block model. This is only with two. This is stochastic block model. You have two characteristic scales. One scale is the scale of the single module, and the other scale is the scale of the whole system. And so you have two peaks again. But the difference between the Watts-Strogatz and this one is that in this case, in the middle, you have not zero. You have a lot of diffusion because you have not a disconnection, then rewiring from disconnected region. You have just some rewiring on some few links. So it also reveals the topological structure. What they say, there is more than the single maxima. This is the Barabasi-Albert network, the preferential attachment with m equal to 1. M equal to 1, that means that you have the preferential attachment in which at each time a new node is introduced in your network. It comes with only one single arm that attach directly to other nodes already present in the network with a probability proportional to the size, to the connectivity already of the nodes, the pre-existing nodes. If you do this, you get not only a scale-free, as you know, a scale-free networks with degree distribution with infinite the variance, that is with k to the -3 distribution of the degrees, but also a scale invariant ones, a scale invariant distribution, so that this is flat. And if you go to see what's the spectral dimension for this case, it appears to be 2. 2 is the spectral dimension 2 is found for random trees, but singular random trees, for which the variance of the branching ratio is diverging. If you do random branching with finite variance of the branching ratio, you get a random tree, and the spectral dimension is 4/3. If you make this to diverge, it becomes 2. So this means that the Barabasi-Albert, topologically, the Barabasi-Albert with m equal to 1 is a tree. You know that everyone knows it is a tree, but it has the same topology of a random tree with diverging branching ratio. Okay, I will skip this and let me go for the 5 minutes to application. So we have seen how to, in this second part of the talk, I just concluded that this susceptibility is able to give you a macroscopic scale of correlation of organization, topological organization of your network. Are you able to do something mesoscopic, not only to reveal the single maxima, but what happens progressively to your system in collecting data? So this means to go to tackle the problem of community detection with a scale parameter. Changing the scale parameter, what is the best partition of the system at this given scale? You choose an arbitrary value of the scale, and you say, what is the best partition for this scale? Okay, this is it's an incredible word in network. It's very difficult to enter the world of community detection because there are so many papers, so many recipes to do community detection that, you know, it's quite conservative subsector of network theory. But anyway, you know, this has been this problem is important for many real world networks. Some example, the brain, but also I don't know, metabolic networks in biology and etc. So the most important tool, mathematical tool, is the modularity introduced by Newman. about 20 years ago, in which you say, what is the best partition of this network in family so that there is the biggest imbalance from internal connection with respect to the external one. What is the best one? Clearly, it's a bit, you introduce this modularity. For each partition, you can introduce a modularity and you look for the best partition. So it's an optimum optimization problem, which is NP complete. And so typically we have just a local approximation of this algorithm. There are other methods, for example, macroscopic stability. What can we do with our method? With our method, very simply, we can use our measure our green function of the diffusion. You fix time t. Then this matrix can define also a Jacquard proximity index, so a certain similarity index. So the larger is this quantity, the closer are the nodes from the information from the transmission on time scale t of the information. Okay, so following this, you can build, and then at each time t, you can build a dendrogram. Oh, you have a similarity index so that you can build the dendrogram. Then the problem is, what is the best cut? What's the best result? All this tree is informative, but what is the best picture, snapshot of the network, the partition? You measure the distance between subsequent branching. The largest one is a measure of is due to the meaning of rho, is the amount of information collapsed in a single quartz granite. So how much information do you burn in a single step of the dendrogram? That is the best partition. That means that you are exactly localizing the intrinsic structure. And we applied this method, and so I finished this the talk in after 2 slides. For example, we analyzed many networks. It works very well. For example, real-world networks. These are metabolic networks for Escherichia coli or for mus musculus. These networks are already classified by different metabolic functions, and you recognize all the functions as the families. Okay. 1 minute. We are able to partition also synthetic networks that have been built exactly to put all the algorithms of community detection in strong difficulty. For example, these are applications of, this is the walk trap, this is the informat. They are not able to reconstruct the families of this fractal network. In our case, it is very simple. You immediately recognize the family. Let me this is the last slide. Okay, Paolo. This is the last slide. Clearly, you can do the best partition at different times. And what happens typically? You can expect that the community will change, the best partition will change with time. What happens in reality in most of networks is that starting from a time on, the partition is quite stable. The best partition is quite stable. There are some networks, for example, this is the Karate Club network that is used as a benchmark for community detection problem. This is the topological organization of the participant to an original karate school that at a certain point split it into schools. Okay, and it's used as a test for community detection algorithm. You want to have a good algorithm able to recognize in this network the 2 schools. Almost all methods works well, the most advanced one, but there is always a problem with a couple of nodes that sometimes, depending on the algorithm, fall in one school or fall in the other school. Okay, so in our case, what happens when we change time? At a certain moment, the 2 schools become stable, but there is a single node, the critical one, there is no literature, that move from one school to the other by changing the diffusion time. Depending on the scales on which you resolve your system, your node will belong to one or the other. We call these metastable state. They are very important. There are few nodes that permit the communicability in the network. So they have important physical meaning. So let me go directly to the acknowledgement to all the collaborators. So Pablo and Tommaso and Guido, that are the way that at the beginning in the formulation of this approach, and then two PhD students, very good, Francesca Santucci and Nathan Boggialini, and Giulio Cimini, I think some of you knows that joined us in this work in the last year. So thank you very much for the attention.